All right, let's dive into the invisible rules that pretty much run our entire world: force and pressure. We're talking about the fundamental pushes and pulls that control everything that moves, from a planet spinning in space to the very blood pumping through your veins. So let's get right into it. I mean, really think about it. We see stuff moving all the time, but what's actually making it start or stop or suddenly change direction? Well, it's not magic. The answer actually boils down to two incredibly simple concepts: force and pressure. So here's our roadmap. We're going to cover this in 6 quick steps. We'll start with the absolute basics of what a force even is, then look at how they can team up and what they can actually do. After that, we'll get into the fascinating world of pressure and cap it all off with a mind-bending fact about the air around us. Okay, first up, the invisible push and pull. Let's get down to brass tacks. What exactly is this thing we call force? You know what? It's really that simple. When you kick a ball, that's a push. When you open a drawer, that's a pull. Even just lifting a book off the table is you pulling it against gravity. Every single action, from flicking a light switch to hitting a home run, it all comes down to being either a push or a pull. And here's the most important part. A force isn't some kind of magical energy floating around. It only ever happens when two objects interact. A car isn't going to move just because you're staring at it. It moves because your hands interact with it by pushing. It's that interaction that creates the force. Okay, so we've got a handle on what a force is. But what happens when you have more than one force acting on the same object? Well, that brings us to our second section: how forces combine. This is actually pretty intuitive. If you and your buddy push a heavy box in the same direction, your forces combine and add up, making the job easier. But if you push from opposite sides, you're literally working against each other. The box is only going to move if one of you pushes harder. That difference between your forces is called the net force. It's just like in a game of tug of war. The rope only moves when one team pulls with a greater force than the other. So forces are pushes and pulls, and they can work together or against each other. But what do they actually do? What kind of changes can they make? That's what we'll dig into in Section 3, A Force for Change. Think of a force as an agent of change. It can take a soccer ball that's just sitting there at a dead stop and send it flying across the field. It can speed that same ball up with another kick or slow it down with friction from the grass. A quick flick from a hockey stick can totally change the puck's direction. And, of course, if you squeeze a lump of dough, you're using force to completely change its shape. And all of this leads to a really key scientific idea: the state of motion. It's a simple term that describes an object's speed and its direction. So anytime something speeds up, slows down, or just turns a corner, it's a force that's responsible for changing its state of motion. Now, it turns out not all forces are the same. They basically fall into 2 major categories. And the difference is super simple. Do they actually have to touch something to work? Let's look at contact versus non-contact forces. Contact forces are the ones that make total sense to us. You gotta physically touch a door to push it open. But non-contact forces, well, that's where things get a little weird, because they can push or pull on something across what looks like totally empty space. So for example, the muscular force you use to lift something, or the friction that slows a sliding book down, those are both contact forces. But a magnet pulling iron filings toward it, or static electricity making a balloon stick to a wall, or even gravity pulling an apple down from a tree, those are all non-contact forces. They're acting like invisible hands reaching out across a distance. Okay, let's shift gears a little bit. We've talked about what a force is, but now let's talk about how it's applied. Because it turns out it's not just about how much force you use, but where and over how much space you apply it. And this brings us to the concept of pressure. It's just force spread out over a certain area. In this simple little formula, pressure equals force divided by area, is honestly one of the most powerful ideas in all of physics. The secret is that the area is on the bottom of the fraction. And here's the perfect way to understand it. Why is a sharp knife so good at cutting? It's not because you're pushing any harder than you would with a dull one. It's because all the force from your hand is being concentrated onto a tiny, tiny area, that razor-sharp edge. This creates an immense amount of pressure. A blunt knife spreads that very same force over a much larger area, which results in low pressure, and it just kind of mashes the tomato instead of slicing it. And once you get this concept, you start seeing it everywhere. You know how porters who carry heavy loads sometimes put a round cloth on their head? They're increasing the surface area to reduce the pressure. That heavy backpack you have has wide straps for the exact same reason, to spread the force over a larger part of your shoulder, which makes it way more comfortable. It is all about managing pressure. All right, for our final section, we're going to look at the biggest, most constant pressure of all. One that's pushing down on you right now from a source you can't even see. Get ready for this one. That's right, the air itself has weight. We are literally living at the bottom of a giant ocean of air called the atmosphere. And the force of gravity pulling down on all that air creates what we call atmospheric pressure. And here is the absolutely mind-blowing part. The weight of the air pressing down on just a small patch of your head, about 15 by 15 centimeters, is around 225 kilograms. That is literally the same as having a giant panda sitting on your head, right now. So why aren't we all just flattened into pancakes? The answer is actually beautiful and simple. The pressure inside our own bodies is pushing outward with the exact same amount of force. The massive push from the outside is perfectly canceled out by the push from the inside. It's a perfect balancing act. And if you want proof of this unbelievable power, check out this famous experiment from the 17th century. A guy named Otto von Guericke took two metal half-spheres, fitted them together, and then pumped all the air out from the inside. With no air inside pushing out, the atmospheric pressure on the outside was so powerful that two teams of horses couldn't pull the spheres apart. That's the insane power of the air all around us. So from the friction that lets you take a step to the gravity that keeps you on Earth, our world is constantly being shaped by these invisible pushes and pulls. The next time you see something move, just stop for a second and ask yourself, what force is at play here? And you'll start to see the hidden architecture of the world all around you.